Hello, class. This is again the recorded lectures continuing in chapter 4, linear regression analysis. I think this is going to be the last one. We'll see how fast I can get through it. So this is going to talk first about taking the equation and using it to do predictions. And so we're going to continue with the same equation with the size of a home compared to the selling price, and taking a look at the equations that we've generated. So let's see where we're at here on the slides. And so here is our equation down here, where we have, right here, where we have y equals 160 and some change plus 0.0992x. And say like you wanted to estimate how much the selling price would be if you had a house that was 3,000 square feet. So here's the beauty of the equation. So the first thing that you want to do is you want to make sure that the predicted number that you're plugging into is reasonably close to what we're talking about with the data. And you look at your data and you say, okay, 3,000 is right in the middle of this almost. So it should give you a very good predictor of the value that you're looking for the actual selling price. So basically, you just get out your calculator and do a little bit of calculation where you plug 3,000 in for X and multiply it by 0.0992 and then add 160 to it, and out comes 457.8. So you can estimate that you would be able to sell a 3,000 square foot house in this area for $4,570,800, right? And so that's what we mean by predictions. And it's a very powerful tool. Engineering world, that's what we did quite a bit, is take data and generate equations to model it. Not always linear in this case, but for the statistics, we just deal with the linear ones. So as I was saying before, that you have to make sure that the data and the prediction is reasonably close. Like, for example, if you wanted to plug something in that you were looking for a 10,000 square foot house, would this model work for this so well? You don't know for sure, right? And that's why you're a little bit more leery when you plug in a value for X, for example, to figure out what value of Y is if it isn't reasonably close to your data set. So if you look at your data set again, it's important to say, okay, well, what would be the lowest number I plug in? Maybe 2,000. You feel comfortable with that? Maybe 2,200, you could argue. You know, it's not perfect science. At the high end, maybe 3,400 square feet. 5,000 looks like it would be way too much. 10,000 would be way out of line. And so you have to be careful when you plug in values. And so that's one kind of idea that we want. And we're not going to go through the rigor details of those types of calculations, but hopefully that concept will sink in. The other concept that I'd like to sink in is the idea of what the stats people call residues. I like to think of it as errors. And what the residue is that if you plug in a value of a data point, what is the difference between the actual model, right, and the actual data point? And the book, and all stats books, calls it residue. I like to think of it as the error between the actual data and the prediction that you would get using your equation as a model. For example, we did this point 2555 and 426. So if you plug in 2,555 square feet into the equation, you would get a selling price of $413,600. But the actual selling price was 426. So what they call residue, I call error. And so what that would be is the difference between the two would be $12,400, for example. And so you could take a look and generate the residue or the error rate for each one of those data points. And the goal is to have it as small as possible. Sometimes if it's really, really big, you might consider one of those points an outlier. We don't talk about outliers in this context, in this class, but if you are doing a regression analysis, the idea of an outlier is also quite important. So the last thing I'd like to introduce, and the book does a reasonably poor job of this, because to me, this is a more important calculation than the correlation coefficient, or R. And in words, it's called the coefficient of determination. But basically what it is taking the correlation coefficient and squaring it. And so most mathematicians use this to determine how good the prediction is. And again, because you square something, it always turns positive. So now we're going to have a number between 0 and 1. And the closer to 1 you get, the better the predicted model is, the better the equation is. And the closer again you get to 0, the worse it is. And this is the idea of looking at the residues or the errors and checking how close they are to the actual values. And so the good news is that your calculator and the spreadsheet give you those values. If you went back to your calculator calculation, I put it on pause because I couldn't find the slide. But if you went back to your calculator calculation here, you could see that we have the R squared value right here as well. So you see you get both of them when you do the linear regression analysis. So on your calculator, you get the equations, 2 coefficients, the A and B, the y-intercept and the slope, and then the R and the R squared, which is everything that you will need to do any of the homework and the calculations in this class. If you go to the spreadsheet, where did my spreadsheet go? Here we go. So the spreadsheet, as I alluded to, when you do the original trend line analysis, right, you end up with the R squared value right there. So if you wanted to find the R from that, you take the square root. And if you did that, you want to make sure you know what the slope is, because when you take the square root, it could be plus or minus, right? So if the slope is negative, it should be negative, and if the slope is positive, it is positive. So if you wanted to calculate R squared from the R value, you just basically take this number and square it. So let me just do that here on Shift 6, 2, and you could see you would get the R squared value as well. So as promised, I do want to show you one more analysis that the spreadsheet does a wonderful job at. And if you did that plugin that I suggested that you do, it is the data analysis. So if you go to data and you go to data analysis, you get all these different capabilities. And one of them is regression. So if you click on regression and you hit OK, up comes data that you would want to enter. And so it's weird because the Y is first, so be careful. So you could enter the Y and the range for the Y range, and then the X for the X range. And if you click labels, you would get the labels. And what's nice is you could do, and we don't do that in this class, but some higher level stats, you do confidence intervals for this, etc. But another thing that's nice is you can get those residues, which is the error from each one of those. So I'm going to click on that. And if you hit output range, I'm going to stick it. I got to click in there first and stick it right there. So if you hit OK, out comes all these numbers. Look how cool that is. And so this is the idea of ANOVA and a bunch of other stuff that we're not going to talk about in this class. But what do we have up here? Here's your R, here's your R squared, and there's also something called adjusted R, which we don't talk about. And then if you come down here, we have our coefficients. There's the intercept, which is the A value. Here's your slope, which is the B value. And here is your residue. So here's each data point. This is the actual prediction using the equation. And then here's the residue or the error for each one of those. So it's really nice. It does all these calculations for you. And so I highly recommend taking a look at that. So that actually ends the recorded lectures for chapter 4.